Hello and welcome to SFU Math 232, Lecture 2. This is linear algebra. My name is Brenna Davison, and today we're going to cover section 2.2, solving linear systems by row reduction. So last lecture we saw how to take a system of linear equations and represent the information in those equations in an augmented matrix. And now we're just going to practice and get some terminology for working with those matrices. So some definitions off of the top here. I am going to, throughout this course, in fact, emphasize the importance of understanding the words that we're using. So when I say something, you get the idea of what I'm saying in your head on the words. So we mean the same things by the words. So we're going to spend a little bit of time here with some vocabulary. And starting on that note, we're going to look here the definition, two definitions, and it's two in this way here. The first definition is going to be of reduced. Well, actually, the first definition will be like this: what is a row echelon form? And then the second definition will be what is a reduced row echelon form. So in order for it to a matrix to be in row echelon form, these following three properties have to apply. So what has to happen is the matrix has to have all three of these properties. Each row consists either of all zeros or has a 1 as its first non-zero entry. And when we do have one of those ones as the first non-zero entry, that entry is called a leading one. Okay. Any rows that have all zeros are grouped together and they're at the bottom of the matrix. So they're the last rows of the matrix. In any two successive non-zero rows, the leading one in the lower row is to the right of the leading one in the upper row. Okay, so if these three properties are satisfied, then a matrix is in row echelon form. If additionally the matrix satisfies this property here, then it will be in reduced row echelon form. Okay, and then that extra constraint is that each column with a leading one has zeros everywhere else. Okay, so just to make sure that we understand what we're talking about here and being able to recognize when a matrix is either in row echelon form or then possibly even more with an additional constraint in reduced row echelon form, we're going to take a look at some matrices and identify if it's in row echelon form, reduced row echelon form, or in neither, and we're also going to identify the leading ones. Okay, so my suggestion is at this point, because we're in this, this is a sort of asynchronous part of the course, what you should do now is stop the video and look at all of these matrices, look at the definition of what those words mean, and identify for yourself which ones are reduced row echelon, which ones are row echelon, and you should circle the leading ones, and then you should restart the video and see whether we get agreement. And perhaps I make a mistake, or perhaps you make a mistake. But any which way, if you get them all, then you can say to yourself, "Yep, I got it. I understand this." If you can't do that, then hesitate a bit before watching me go through it, and take a careful read through what the criteria are, and then try to look at the matrix and ask yourself, does criteria A apply? Does criteria B apply? Does like that until you see whether you have all the criteria for one or both of these conditions, or maybe the matrix is not either. Okay, I'm going to go through. I don't know if I'm going to do it exactly in order because some are more obvious than others. So I'll just start here with this matrix right here. Let's start with this one here. This is actually, we're going to see a very important matrix. This is an identity matrix, and this one is in reduced row echelon form. So I'm going to just write below here, it's in reduced row echelon form. Okay, there is a leading one. Let me just circle the leading ones. There is a leading one like that. Those are the leading ones on each row. There's no non-zero rows, so we don't have to worry about that. And each row consists of all zeros or has a 1 on its, so I'm now reading this one up here. Each row consists of either all zeros, no, or it has a 1 as its first non-zero entry. Okay, so these are the rows this way. So each row here is non-zero, and the first element that you encounter when you're coming from over reading from the left is a 1. So okay, we don't have to worry about part B because there's no non-zero rows. And then in any two successive non-zero rows, so let's just pick two successive non-zero rows in this matrix. Let's just pick these two, for example. And you'll see that this leading one here is to the right of this leading one here. Okay, so it satisfies that. And then, so it's for sure in row echelon form. And then the further criteria here, let me just get a different color for that, black. The further color here is that this is a 0, and then these two things are 0. So in any column that has a leading 1, so I mean in this case all of the columns have a leading 1, in fact, so why don't we circle all the zeros that are necessary. Any column that has a leading 1, so say for example this column has a leading 1, we circle the leading ones. That column has a leading 1, and everything else in the column is 0. So that one's in reduced row echelon form. Okay, let's take a look at the next one. This one is neither. I'm going to go in order here. This one is neither. Why is it neither? Because look at what happens here. Row 2, there, row 2, and here, row 3. You notice that row 3 is a lower row than row 2, and you notice that this one right here is not to the right of this one here. Okay, so that this one is in neither. I could swap those two rows. Let me just do that. 1, 0, 0, 5, 0, 1, 0, 4, 0, 0, 1, 3. Okay, I've swapped those two rows. And I now have something that is in reduced row echelon form. Okay, I'm going to circle the leading zeros. So as it was originally, it was neither, but now I've got leading zeros like that. There's no 0 rows. I have that the leading ones move to the right as I go down, and any place that has a leading 1 has zeros everywhere else. So now by swapping those two rows, I've got it down here into reduced row echelon form. Okay, it wasn't though originally. Okay, let's move over to the next one on the list here. This one here, I'm going to circle the leading zeros as leading ones. Apologize, leading ones. There they are. And so I see that it's in row echelon form, but here I've got a 2, and because of that, it's not in reduced row echelon. So this one is in row echelon. Okay, let's move over to the next one. I will circle the leading zeros, the leading ones, and then I see that this guy here is a 0. So this, in fact, is in reduced row echelon form. Okay, next one over, I see a row of zeros, and it's not at the bottom. So this one is neither. I keep moving down here. I will circle the leading zeros in this, leading ones on this one. For some reason, I want to always say leading zeros. The leading ones there, and I see that the last row, it's not to the right, like row 3 here. The one in row 3 is not to the right of the one in row 2. So therefore, this one is also neither. Again, I may be able to swap rows and fix the problem, but as it stands, it's neither. Okay, next one over. Leading 0, leading 1, leading 1, leading 1, and leading 1. I see that the 0 row is at the bottom. The leading ones move to the right as I go down. I see that there are zeros in the columns that have, so here's a column with a leading 1, those are all 0, and here's a column with a leading 1, those are all 0. Here's a column with a leading 1, and those are all 0. So in fact, this one is in reduced row echelon form. Okay, moving to the next one, we have leading ones. We have the row of zeros at the bottom. The leading ones are moving to the right as we move down. However, we have this guy here, this 1 right here. So this is in row echelon form, but it is not reduced. So this is row echelon, like that. And then let's look at the last guy here. I got a leading 1 there, a leading 1 here, and like, there's a 4 here. Okay, so the first number in that row is a 4, and we have this here. Each row consists of either all zeros or has a 1 as its first non-zero entry. So that fails on the 4 here. So that is a problem. So this is neither. Okay, so the idea at the end of this is that we've defined 2 terms, row echelon form and reduced row echelon form. We should know the properties that define those types of matrices, and we should be able to pick out from the any matrix which of those forms it's in, or possibly neither. We've also introduced the term leading 1. We've also got the idea of like row 1. This is like row 1, row 2, row 3, and then here we've got columns. That's column 1, column 2, column 3, column 4. Okay, so we have in our matrix we have rows and we have columns. Okay, so the good news is, if we've represented a system of linear equations, and we can notice, or we can put the matrix into reduced row echelon form, then we can immediately read off the solution to that system of linear equations. Okay, so here's a system of linear equations with variables x, y, and z, and this is an augmented matrix. So oftentimes you'll see I will add this line here to indicate clearly that it's an augmented matrix. So just because we're getting started with this, I'm going to write out the equations that this augmented matrix represents. Okay, it looks like this. x1 plus 0x2 plus 0, it says x, y, and z. Let me try it again. X plus 0 times y plus 0 times z is equal to 5. That is what the first row is telling me. That is the first equation in this system of linear equations. The second equation is telling me that 0 times x plus 1 times y plus 0 times z is equal to -2. The third equation is telling me that 0 times x plus 0 times y plus 0 times z is equal to 1. Okay, so immediately I see actually a problem right here. And I will notice this problem whenever I see this at the bottom. So this is telling me I take 0 and I multiply by any number x, and I take 0 and multiply, and somehow that is supposed to come out to 1. That's not going to be possible. So this is not possible. Not possible for any x, y, or z. So this system has, therefore, this system has no solution. Okay, I'm going to just change the matrix just a bit and show you what it will look like in reduced row echelon form when you can easily read off the solution. So let me just get the same basically almost the same matrix here. I'll write out the equations, and then put that. I'm going to put a 1 there. Okay, that's the only thing I changed. I changed this number from 0 to a 1. Now, this augmented matrix has this system of equations. X plus 0 times y, it's like 1 times x, if you will. 0 times y plus 0 times z is equal to 5, coming from row 1. 0 times x plus 1 times y plus 0 times z equals minus 2, coming from row 2. 0 times x plus 0 times y plus 1 times z is equal to 1, coming from row 3. Okay, so 0 times something is 0. So let me just rewrite these. X equals 5, y equals minus 2, and z equals 1. So in this case, with this slightly changed augmented matrix here, I get a unique solution, and there it is. So the solution is unique, and I've got it represented there. Okay, so you can see what's happened. If you take your system of linear equations, you form an augmented matrix, and then if it is possible for you to put it in reduced row echelon form, you can simply, right from there, read off the solution to your system of linear equations. Okay, so let's take another look. We're gonna here's a system of linear equations. Let me identify the leading zeros in this one. We know it's in reduced row echelon form because we were told. Let me just maybe check that while I'm doing this. But I will just identify those leading zeros, leading ones. Good grief! I don't know why I want to say it as a 0. The leading ones. So there's the leading ones. I see that there's zeros in the columns that have leading ones elsewhere. So this indeed is in reduced row echelon form. And it's, let me just write out the equations in the same way. I'm not going to always do this, of course, but just as we're getting used to doing this. So the, just kill that. Sorry about that. So the first equation coming from row 1 says that x1 plus 2x2 plus 0x3, so I'm going to leave that out, 2 plus 2x3 I got x2, oh sorry, x3 has got a 0 in front of it, and then 2x4 is equal to minus 3. Let me put that vertical bar I sometimes put in there to indicate that it is indeed an augmented matrix. So that is the equation for that first row of that matrix. And then let me get the equation out here for the second one. That's going to be x3 minus 5x4 is equal to 8. And then let's look at that third equation that's represented in the matrix there. That's basically telling me 0 equals 0, or 0 times x1 plus 0 times x2 plus 0 times x3 plus 0 times x4 is equal to 0. Well, I mean, any values of x1, 2, 3, and 4 will work for this. So then now the next thing we're going to be noticing is that we have, because this first column, C1, has a leading 1, and this column here, C4, column 3 here has a leading 1. That is corresponding to these variables, 1 and 3. Okay. So this tells me that x4 is a free variable. It isn't going to matter what is x4. It also tells me, in fact, that x2 is a free variable. But I'm starting down. I'm starting from the bottom here when I'm looking at this, and I'm looking at this here, and I'm seeing that any value for x4 will do. Okay. There, and also I'm noticing that there is no column. There's no column 4 with a leading 1. Okay, so that is telling me that x4 is a free variable. It does not matter what it is. So I'm going to write that like this: x4 is a free variable, and I'm gonna then say let x4 be equal to t, where t is any real number. Okay. Then I'm going to look at the line above. I've already written that out actually. It's x3 minus 5x4 is equal to 8. And that is the same as saying x3 is equal to 8 plus 5x4. And x4 I've identified as this free variable t. Okay, that is what I have dealt with this line here, and I've dealt with this line here. Now I'm thinking about x2, but there is no column where the number, there's no, column 2 does not have a leading one. Okay, or if you want to look at this, there, like row 2 does not have a 1 in the second column. So that means that x2 is a free variable. Doesn't matter what it is in that sense. We are in this situation, in the solving this linear system, that we have an infinite number of solutions. Okay, we have we're going to see theorems backing this up, but basically when we have a system of linear equations, there's 3 possibilities: no solution, unique solution, or infinite number of solutions. We've already actually seen an example of no solution, and we've seen an example of a unique solution, and this is an example of the third possibility, an infinite supply of them. So I'm going to assign a free variable here. Let x2 equal to s, and s will also be any real number. Okay, now I'm going to take a look at what x1 is. x1 is equal to minus 3 minus 2x2, which is s, minus 2x4, which is t. Okay, let me box in the things I think are important of what I've said here. That is x4 is t. I'm trying to provide you with an answer for x1, x2, x3, and x4. x2 is this, x1 is this, and x3 is this. Okay, that's what I've done. I've identified what the variables are, and I'm going to write this out in a slightly different form. And I'm gonna write it in this manner. I'm gonna make what I'm gonna call a column vector. We're gonna see more of this coming. I'm gonna write it like this. What do they look like? Well, let's see. x1 is minus 3. Well, I'm gonna write it like this, and that's going to be s times something and t times something. I've got 2 potentially free variables. I do not potentially, I have 2 free variables. Okay, and I see that x1 is minus 3 plus minus 2s plus minus 2t. What is x2? x2 is equal to s. Okay, so just reading across. x2 equals 0 plus s times 1 plus 0 times t. Okay, how about x3? x3 is 8 with no s's and 5 t's. And how about x4? x4 is 0, 0, and 1 because x4 is t. Okay. All right. So what you what you can do now is for the system of linear equations represented by this augmented matrix, you can choose any value for s and t, and you will generate a solution. So let's just do an example. So any values of s and t will do. So consider s equals 1 and t equals 2, for example. That would mean, according to my calculations here, that x1 would be equal to what? Minus 3. I'm going to write it out longhand for this one. Minus 3 plus s, 1, times minus 2, plus t, 2, times minus 2. Okay, so then I do that calculation, And what do I get? X1 is minus 3, minus 2, which is minus 5, minus 4, which is minus 9. Okay. And I similarly go through and I calculate what is X2. Well, X2 is simply S. And then X3 is 8 plus 5t. And t is 2, so that's 18. And X4 is simply t. So that's 2. Okay, so there is a solution to my system of equations, one solution. Like I said, in this case, because we have a free variable, we have an infinite supply of solutions, but there is one of them. It's right there. Okay, you could now try this out if you want. I mean, we know that what's supposed to happen, for example, is given our system of equations, we know that x3 minus 5x4 is supposed to be equal to 8. Well, let's see if that works. 18 minus 5 times 2 is, that's 18 minus 10, which is 8. Ding, ding, it worked. Okay, so try another value of s and t. Generate another solution, check that the solution satisfies all the equations. I mean, that's what a solution to a system of linear equations is. It's a set of numbers that when you plug those numbers in to all of your equations, they are all true. Okay, so try another value of s and t. Okay. All right, now here we have a matrix. It's not in reduced row echelon form. It is, however, in row echelon form. That's that capital RE, row echelon form. It's an augmented matrix, and it's not in reduced form because of why? Because of this guy right here. And let's see, that's the leading one. I'm going to circle those ones. 1, 1, and 1. Those columns are supposed to have zeros everywhere else, and they do not. So that would be, the problem would be, hang on, I need to get a different color. The problem would be then with this one and this one. Okay, so what we're now going to do is attempt to start with this row echelon form, and we're going to be using a procedure that's called back substitution. Okay, and the steps that we're following is actually at the bottom here. Express the leading variables beginning with the bottom and working upwards. Substitute, assign different parameters to all free variables, if any. So express the leading variables. So which columns do we have ones in? We have a 1 here, a 1 in this column, and a 1 in this column. So what are the leading variables? The leading variables are x1, x2, and x4. That means that the free variables are the rest. Free variables, x3. Okay, so then we start at the bottom, and I think I'm gonna erase this just so I can refer to it again. So we're gonna start at the bottom. And we're gonna, by that I mean we're gonna start here with row 3, and we're gonna see what does row 3 tell us. Row 3 right here tells us this is an augmented matrix. It tells us that x4 is equal to 3. Okay. Then we have already identified that x3 is a free variable, so I'll express that like this. x3 is any number t, where t is a real number. And then I move to the next row, this one here, and I'm going to write out what that's telling me there. That's telling me x2 is equal to minus a half plus 2x3 plus 3 halves x4. Now I'm going to substitute for x3 and x4 because I've just identified in the previous two steps what x3 and x4 are. So this becomes minus 1/2 plus 2 times x3 plus 3/2 times x4. And then I do some arithmetic, hopefully not making a mistake. 2 plus 9/2. And 9/2 minus 1/2 is 8/2. That is 4. So I get here that x2 is equal to 4 plus 2t. Okay, and I proceed with x1. Now I'm moving to the next row that has a leading 1, and that is the first row. And that row is telling me that x1 is equal to 3 minus 2/7 x2 minus 3/7 x3 minus 2/7 x4. Now I substitute for x2, x3, and x4, which I have just previously found out. So by starting at the bottom, I can figure out what is x4, and then I go to the next one, and I can figure out what is x3, possibly in terms of x4, and then I can use my answer for x4, and I just kind of keep working back up. That's why it's called back substitution. So I'm working backwards, and if you want to look at it that way, I'm working from the bottom up, and at each step I'm substituting for what I've already figured out from the previous step. Okay, so let's do that now here for x1. That's going to be 3 minus 2/7 times x2. x2 previously noticed to be 4 plus 2t. And then minus 3/7 and t, x3 is t. And then minus 2/7 and x4 is 3. Okay, and then I put all this together. 3 minus 8/7 minus 4/7 t minus 3/7 t minus 6/7. A little bit more arithmetic. I get 3 minus 2 minus t, and a little bit more, and I get 1 minus t. Okay, so that's what I've now figured out x1 is. x1 is 1 minus t. Okay, I am going to box the important things that I found out. I found out that x4 is 3. I found out that x3 is free. I found out that x2 is 4 plus 2t, and I found out that x1 is 1 minus t. Okay. So now I will write this in the format I wrote the previous solution in. It looks like this. Okay, that's my solution vector, and it looks like this. X1 is, that's this one. X2, that's this 4. X3, this is going to be a 0. There's no constant term there. And then x4 is 3. That's this 3. And it's going to then be plus t times x1 minus 1, x2 plus 2, x3, 1, right? 1 times t, and x4, no t's. There it is. Because that is the solution to this matrix that we got presented with, which was in row echelon form. It was not fully reduced though. Okay, but so we had to use this procedure of back substitution to get a solution out. It was a little bit more complicated. If you get a matrix in reduced row echelon form, it is very straightforward to write down the solution of the corresponding system of linear equations. If you get it in row echelon form, it's still not too bad, but you do have to do this back substitution. Guess what we're going to handle next? That's when you just get hit with a matrix and it's in neither of those forms. You have to do something. So what we're going to do is a procedure called Gaussian elimination. So the object of Gaussian elimination is to take some arbitrary augmented matrix like the one we have here before. There it is, an augmented matrix, and to convert it to row echelon form. That is the purpose. Okay, so we're going to be able to the procedures outlined for us here. What we're going to be doing is what we call sort of legal elementary row operations. And we're going to delve a bit more into what that means. But as I'm doing these row operations, let's think in terms of the system of linear equations, what it is I'm doing. Okay, so the procedure for doing the Gaussian elimination says step 1, locate the leftmost column that does not consist entirely of zeros. Okay, let's point to that in this step. There it is. Step 2, interchange the top row with another row if necessary to bring a non-zero entry to the top of column C. No, we don't need to do that. Interchange the top row with another, if the entry in the top row and column C is an A, multiply the top row by 1 over A in order to introduce a leading 1. Okay, so we don't need to do that either because we've got a 1 here in the leftmost upper position that's possible for the matrix as it is. Okay, then what we're doing is we're going to add suitable multiples of the top row to the rows below so that all of the entries below leading 1s become 0. Okay, so the object of the game right here is to make all of these entries to a 0. How do I do that? What did I do to do that? I took, and I'm going to write it out here, I took the second row. You see how there's, you see, okay, here's the second row here. And you see how different the second row is looking right here. How did that happen? I take row 2. In order to get that new second row, I'm taking row 2 and I am subtracting from it 2 times row 1. Okay, I'm going to draw the matrix here and see if we can get that. Row 1 is not changing, so it's 1, 2, 3, 4, 1. I'm going to put those bars into. I like the bars. Okay, like that. And then I'm taking row 2 and I'm subtracting row 1 from it, and I'm putting that back into row 2. Usually I'll indicate that like this. Row 2 becomes row 2 minus 2 row 1. Okay. So this number here is actually 2 minus 2. Okay, and this number here is 4 minus 2 times 2. This number here, this third number, is 6 minus 2 times 3. And then the last number is, hang on, 2 minus 2 times 4. And then this one here is 2 minus 2 times 1. Okay, that's how that's happening. So I'm taking row 2 and I'm subtracting 2 times row 1. And I'm getting these numbers right here. Let's go to the next row. Next row, what am I doing? The original row 3 is going to be replaced by row 3 minus 2 row 1. Okay, and I get the answer that I have here. And then in my next row, what am I doing? I'm saying the fourth row, so row 4 is going to become row 4 minus 2 row 1. Okay, and you should fill in the entries here of the calculation so that you make sure that you know what you're doing. Okay, and why am I allowed to do this anyhow? So let's just consider a different example. Imagine I have some system of equations that look like this: x plus y plus z equals 2, 2x minus y plus 3z equals 4, and I don't know, doesn't matter. X minus y plus 6z equals 2. Okay, that's a system of linear equations, which I could represent with an augmented matrix. Now, the reason I can take one, we would be sort of thinking of this as row 1, right? Row 2 and row 3 in our augmented matrix, if we were to put this into an augmented matrix. Now, what if I add together this one and this one? Let me just leave the first one alone. X1 plus X plus Y plus Z equals to 2. And then I'm going to add these two equations together. Okay, that will give me 3x, there'll be no y, plus 4z equals 6. And then the last one I'm going to leave unchanged. X minus y plus 6z equals 2. So now this is row 1, this is row 2, and this is row 3. Because I have just taken simply two equations and added them together, and they were equal on the left and they're equal on the right, this new system of linear equations is actually not new. It is a system of linear equations for which the solution is the same as the original three equations. If you don't believe me, try this out, right? Solve both of these, try them out, and see that the solution to whatever the solution is to this three system of linear equations is exactly the same as the solution to these three. The solution does not change by me adding a multiple of one equation to another one. And that's exactly what I'm doing here in step 4. Also, here in this thing here, interchange the top row with another row. Okay, think about what that means. Here's another system of linear equations. X plus y equals 2, 3x minus y equals 5. Okay, that's system 1. Here's another one. Clearly those two have the same solution set. All I've done is write the equations down in a different order. That's what allows me to interchange one row with another. Okay? All right, and then let's take a look at this step 3. What is this step 3 in terms of thinking about it as equations? What is this step 3 telling us? I have some linear system that looks like this, and instead I decide to write it like this, multiplying the top one by 2 and leaving the bottom one alone. Okay, both of those, this has the same solution as this, and this has the same solution of that. So these little instructions that are here are not mysterious. They are things that we can do to our equations that does not change the solution set. The three numbers or the two numbers that solve our system of linear equations remains the same when we do these operations. That's what allows me to do that. Okay, so now I'm here in step 4, and it says here, cover the top row, and if there are any non-zero rows left, repeat step 1. So what I'm sort of thinking about doing is covering the top row. It's not gone, but I'm kind of covering it up, and I'm looking, and what do I notice then at that point? I notice that there's a 0 here, but there's a 9 here. Okay, so I need to do an exchange. So my next step here would be exchange rows 2 and 3. That's step 2. Okay, and then I write the matrix. It's a matrix that is representing a system of equations, and the system of equations this matrix represents has the same solution set as the previous one. I've only just changed the order that I'm considering the equations in. Like that. Okay, so that was exchange rows 2 and 3. Then, according to my instructions, I want to make this guy here a 1. So I'm going to now introduce a little bit of notation. I'll sometimes go like this. And what am I doing? I'm saying that R2 is going to become 1/9 R2. This is multiplying both my side of my equations by 1/9. Okay, then I'll rewrite the matrix. like this. I haven't done anything to the top row, so I just simply copy it over. What I am changing R2, I'm multiplying by 1/9, so I multiply all the entries here by 1/9. And then I haven't done anything to row 3, and I haven't done anything to row 4. Okay, and then I take a look. Let me just circle the leading ones for us at this point to see where we're at. I've got a leading one here, and I've got a leading one here. Okay, so then what do I do then? I look down to the next row. I sort of, if I would cover up rows 1 and 2, and I look down to the next row, and I observe this thing here, and that is not a 1. So then I decide that I should multiply. So I'm going to now change row 3. Row 3 is going to become minus 1/6 row 3. So I'm multiplying both sides of that equation by minus 1/6, and I get the next version of this system of linear equations, the solution set to it. I haven't changed row 1. I have not changed row 2. And I have multiplied this by 1/6. And I haven't changed row 4. There it is. And now what do? I am looking at this column right here, and I am wanting to make this here into a 0. Right? It is below that 1. So everything below that leading 1 has to be a 0. How do I do that? Well, I take R4 and I add 6. I'm going to take R4. R4 is going to be changed. It's going to be changed into R4 plus 6R3. Okay, so I go ahead. I'm changing row 4, so that means row 1, 2, and 3 are going to stay the same. R4 changes to R4 plus 6R3. Let's see what happens. I get here. Sorry, 0. And R4 is R4 plus 6, or 3, this is a 0. 6 times 0, there's 0. I think I have a slight error in my notes here. I'm just making a note to myself. Okay, there I am. And now I can stop because I am in reduced, not in reduced, stop. I am in row echelon form. Okay, I've got leading ones. They're all going over to the right. The all 0 row is at the bottom. And yeah, there's leading ones on each row, and there's they're going over to the right, and the row of zeros there is at the bottom. Okay, it is not in reduced row echelon form yet. Why is it not in reduced row echelon form? We still have more work to do, but we we recognize that this way. We look at the columns that have ones in them, that have leading ones. Those are these columns. So this harks back to at the beginning of the lecture where we wanted to recognize what's going on. So in those columns I've indicated with the green arrows, this would have to be a 0, and these two things would have to be a 0 for it to be in reduced row echelon form. So the Gaussian, what we call the Gaussian elimination, takes any matrix. We follow these steps, these 3 elementary row operations. We follow those steps until we end up in row echelon form. That's what we call Gaussian elimination. If we add this guy's name to it, Gaussian Jordan elimination, what we want to do is to go further and take the row echelon form that we've got here and do some more operations and get it down to reduced row echelon form. So this, we've already just, that's what we just did, the Gaussian elimination. We just did this. So now we do what we call the backward phase. This corresponds to the backward substitution that what we saw earlier. So now the backward phase, what we're going to do is we're going to start with the last non-zero row, and we're going to work upwards, adding suitable multiples of each row to the rows above to introduce zeros above the leading ones. Okay, so we're going to here take the backward phase here. So we don't have to do anything here. We don't have to do anything here. Okay, don't even want to indicate that. So our first problem, we're starting from the bottom. Our first problem is to notice that we need to get rid of those two. So what we're going to do is go like this. R2 is going to become R2 plus 1/3 R3. So when we're trying to clear this guy right here to a 0, we want to do that using this row right here. Okay, so that's our object. Okay, and we'll perform that operation. What I advise you to do actually is if you've caught what I'm doing here, I would advise you to finish this example on your own and then check your answer rather than just watching me do it. Okay, so but I'll fill in the numbers here. Okay, so R2 is changing. That's the row we're changing. And this is how it's changing. So let's just, for example, take a look at that. What is that? That is minus 1/3 plus 1/3 times 1. That's how that number is getting changed. And then we haven't changed row 3 or 4, so we just simply copy that over. Oh, there they are. Okay. Now, what did we get out of this situation? What we got out of it is that this number right here is a 0 where it wasn't before. Now we want to work on this guy right here. We want that guy to also be a 0. What we're trying to do is get zeros in the columns that have leading ones, everywhere else except the leading one. Okay, here's our leading ones. Okay, so in those columns, these columns with leading ones, we are attempting to get zeros everywhere else. This is the Jordan part of the Gauss-Jordan elimination. Okay, how do we do that? Well, let's look at a row operation that we can perform here. What we're going to do is we're dealing with row 1. So what do we want row 1 to become? If we take row 1 and we subtract 4 times row 3, so I'm thinking here row 1, this guy here, I'm thinking if I subtract 4 times this, that'll get me the 0 that I want. So I perform this operation, replace row 1 with row 1 minus 4R3. Looks like this, 1, 2, 3, 0, 1. And I haven't done anything to rows 2, 3, or 4. So that is 0, 0, 1, 0, minus 1, 0, 0, 0, 1, 0. And then I had that row of zeros at the bottom. Okay. All right, so now look what's happened. It's very exciting. This column here is I've now got it so that with that leading one that I have, this one, everywhere else in the column is a 0. That is already the case for this. And then I look for my other leading one and I see, okay, this guy is the remaining issue. What do I do to get a 0 into that boxed in 3? And what I am going to do is do this. R1 will be replaced with R1 minus 3R2. Okay, that's going to do it. Okay, so let me perform that operation. I'm gonna perform that operation, I am changing R1. That's going to then be 1, 2, 0, 0, 4. And then I haven't changed R2, 3, or 4, so I'm simply copying those ones. There it is. Okay, now let's take a close look at this matrix. I've got my leading ones. It's in reduced row echelon form. I have got a leading one in column 1, in column 3, and in column 4. Okay, so now I can simply read off, starting from right here. The row of zeros isn't giving me any information. I can read off here that x4 is equal to 0. And then I move up. I see that, hang on a sec. Have I made an arithmetic error? Well, I'm hoping I haven't made a arithmetic error. If that is the case, because something's striking me and be slightly wrong, but I can't, let me just assume that I have not made an arithmetic error and then write out what the solution is here. I've got x3 is equal to -1, and I've got x2 is free. X2 is free, so that means x2 will be equal to t. And x1 plus 2x2 is equal to 4. So that means that x1 is equal to 4 minus 2t. Okay, and then I have a solution, which I would write like this: x1, x2, x3, x4, and that is going to be x1 is 4 minus 2t. And that is x1, x2 is t, x3 is -1, and x4 is 0. Okay, so I would write the solution like that. Okay, so the idea is we take any matrix, an augmented matrix representing a system of linear equations. We use Gaussian elimination to get it to row echelon form. Then we can continue and use the Gaussian-Jordan elimination to get it to reduced row echelon form, at which point we can simply read off the solution to the system of linear equations. And this is an algorithmic way of solving systems of linear equations. And we are going to use this a ton. So I'm going to give you obviously some assignments to practice doing this. You got to do it a few times. Maybe, I don't know, how many times do you have to do this? I don't know, 20 or 30 times, maybe something like that in your life. And then you say, oh, I see what I'm doing. I got what I'm doing. And then whenever you need to employ this skill, you simply employ the skill. But you need to do it some number of times so that you get familiarity with what's going on. Okay, we're going to get lots of practice. Okay, let's just a little bit of nomenclature here, a theorem. I've already, in fact, in some sense said this, but I said it in a different way. Every matrix has a unique reduced row echelon form. Okay, that is, pay close attention. That is reduced. If we just have a row echelon form, that's not unique. But all the row echelon forms have the leading ones in the same position of the matrix. So, I mean, now glance back through your notes that you've taken and check that these two things apply to everything that we've done. Okay, and then we're going to have a couple of more definitions. We're going to have what's called a pivot position or a pivot column. And so the pivot positions are where the leading ones are, and then the pivot columns are the columns that contain those leading ones. Okay, so let's just take a couple of examples to illuminate that that bit of vocabulary here. Here's a matrix. I'm just going to randomly make a matrix here. There we have a matrix. Okay, I'm going to do what I've been doing many times. I'm going to just circle those leading ones. I can see that this matrix is in row echelon form. And what I have circled, these ones here, these are the pivot positions. So let's just make that hopefully obvious. Pivot positions. That is this, 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 and that. Those are the pivot positions. And then the pivot columns are these columns. So column 1, column 2, column 3, and column 4 are pivot columns. So this is in row echelon form. Okay, that's the thing. Every column is a pivot column. And there are no free variables. Okay, let's take a second example. There's a second example. Let's circle those leading. Okay, it's in row echelon form. The pivot positions. Okay, those are the pivot positions. And then the pivot columns. Those are the pivot columns. Okay, and what do we know? Column 2 is not a pivot column. Okay, and so that's telling us that x2 is a free variable. And it is telling us also by process of elimination that x1, x3, and x4 are leading variables. Okay, so the idea, the overarching idea here is that we take a system of linear equations, we form the augmented matrix, and we now have a procedure for taking that augmented matrix, doing elementary row operations, putting it into reduced row echelon form, and from the reduced row echelon form, we can see whether the matrix, whether the solution to those system of equations is a unique solution, no solution, or infinitely many solutions. We can see which variables are leading variables, which variables are free variables, and we can write out either the answer to the solution to our system as it's inconsistent or there is no solution. We can write there is a unique solution and here it is, or we can write there is infinite number of solutions and here they are parameterized by our free variable. Okay, a lot to take in on this lecture, and definitely some practice will be required on this stuff. And so anyway, that is all for now. I will be back with section 2.3 next time. Thank you. Bye.